The following content is supported by victoris.org.
So for the next example of dynamic programming, we have static sum. Specifically, we'll focus on the one-dimensional static sum. Sometimes on the internet, you'll see it called prefix sum. Here's the problem for static sum. You have an array of a particular size n, and you have a bunch of queries as well. Each query consists of two indices s and e. To answer the query, you need to find the sum from index s to index e. So for example, if the array A is 1, 4, 2, minus 2, 5, then the query from 1 to 3 would be a of 1 plus a of 2 plus a of 3, which is 4 plus 2 plus minus 2, which is 4. We need to answer these queries in O n plus q time. The code for the naive approach will look something like this. We input the two indices, and with the answer variable keeping track of the current sum, and we're just looping through the array. At the end of it, we'll output the answer. And we repeat these 4 lines for all the queries. However, the time complexity for this is OQn, because this for loop has a worst case time complexity of On, which is the size of the array, and this for loop has a time complexity of OQ, which is the number of queries there are. Now, if Q and N are 10 to the 5, then this would TLE because the usual 1 or 2 seconds time limit only allows around 30 million operations on most judges. This is where we can use DP, specifically the static sum technique, in order to speed up the process. First of all, what does static sum mean? Static means that the array's values do not change over time. The queries are only asking for the sum of the array values, and they're not changing the array values. This property will be important for the application of the static sum technique. However, if the elements do change over time, then we can use another data structure known as the Fenwick tree, which will be covered next time. So how does the static sum work? For each index, we pre-compute the sum from the first index, which is index 0, to the ith index. What this looks like is as follows. If we have the following array A, then the static sum array will be calculated as such. Static sum index 0 will be equals to a of 0, which is just 8. Static sum of index 1 will be equals to a of 0 plus a of 1, which is 9. Static sum of index 2 will be the sum of these 3 array elements, and the pattern continues. So how long would it take to compute this static sum array? The naive approach would be that for each index in the static sum array, we have a for loop that loops through all these yellow elements to sum it up. That will incur a total of On squared time because there are n elements in the static sum array, and for each one of them, we incur On time to compute that value in the static sum array. However, we can make an observation to improve this time. It goes as follows. SS of 0 is still a of 0, and this can be computed in O1 time. When we go to SS of 1, instead of taking a of 0 plus a of 1, we actually take SS of 0 plus a of 1. This would once again only cause one operation, and we see that actually for all the elements in the static sum array, we can compute it in O1 time instead of On time. This is because the green box over here, SS of 5, is equals to a of 5 plus SS of 4. Right? So the green box is the sum of the two yellow boxes. So basically we have saved some time by not recomputing this yellow 5 over here because it was already computed previously. So the pre-computation will be On time. Now suppose we have a query that asks for the sum from a of s to a of e. Instead of doing a for loop that goes from index s to index e, you can simply compute the sub-array sum as the difference of the two green elements over here. In other words, 1 plus minus 10 plus 2 is equals to 1 minus 8. This works because SS of 3, which is this green one over here, is a sum from a of 0 plus a of 1 plus a of 2 plus a of 3. And SS of 0 is a of 0. So if we take SS of 3 minus SS of 0, then we're simply cancelling away the prefix that we do not care about. And that gives us the sum of this sub-array. This is just a single subtraction, so it can be computed in O1. And so now we can answer queries in O1 time. A total of Q queries, so now instead of OQn, we've improved the time to OQ plus n, and that passes the limit. The code looks as follows. Specifically, the base case would be SS of 0 is equals to a of 0, and the transition for the static sum array would be SS of I is equals to SS of I minus 1 plus a of I. Do note that this is starting from I equals to 1 because the base case of I equals to 0 is already written over here. Now for the queries, we return static sum of e minus static sum of s minus 1. However, we need to be careful of the case where s is equal to 0, and in that case, right, ss of minus 1 would crash the program. So we need to put in this conditional to handle the edge case. If we find the 0 indexing edge case annoying, then we can actually conveniently use the following trick, which is to make our array one indexed. And this way, because ss of 0 is equal to 0, right, in the pre-computation step, ss of 1 equals to ss of 0 plus a of 1, it simplifies to ss of 1 is equals to a of 1. And for the query, if we query from index 1 to index of x, then the difference ss of x minus ss of 0 is effectively ss of x alone, because ss of 0 is 0. This way we save our time writing 2 additional lines. Here are some questions that you can use to practice on the static sum. Now, is it possible to extend this to 2-dimensional static sum? Certainly. We can use the principle of inclusion and exclusion, and the idea goes as follows. If we want the sum of a sub-rectangle, then that can be calculated by sums and differences of 4 sub-rectangles starting from the top left corner. Specifically, ss of xy stores a sum from a of 1 and a of 1 to y. So as an example, suppose we have the following array. Most of the array elements are 0 except for the following red squares. Then this table over here is a 2D static sum array. For example, we look at this green square over here at the bottom. This is 3 because it contains all 3 red squares. If on the other hand we look at this square over here, it is 1 because the sub-rectangle from the top left to that cell only contains 1 red square. So for example, ss of this square is equals to the sub-rectangle sum from the top left to that square. And we calculate this for every single square in the 2D grid. Now suppose we want to query the following sub-rectangle. We can calculate it by taking the yellow rectangle, which starts from the top left and ends over here, minus the green rectangle, which starts from the top left and ends over here, minus the green rectangle again, that starts from the top left and goes over here, plus the blue rectangle. And the reason why we need to add back the rectangle is because when we subtract away the 2 green rectangles, we've accidentally subtracted away the blue rectangle twice. So we need to add it back, and this is a concept that we see in the principle of inclusion and exclusion. So visually, the yellow rectangle is A minus B minus C plus D. This can clearly be extended to 3-dimensional static sum and beyond. Pre-computation can be done in OHW, where H is the height and W is the width of this grid. And then we can answer queries of sub-rectangle sums in O1 time, because it's just 3 arithmetic operations. Here are some questions that you can work on for 2D static sum. Next, we'll talk about the longest increasing subsequence.